Hello guys, welcome on Tesla Adventures. In this video, we'll discuss a common concept of thermodynamics and solids, which is thermal stress. So you can imagine that there is a rod. This is a rod which is restricted between two walls, and the gap between these two walls is just enough so that rod is just fitted into the gap of the walls. So if the natural length of the rod is L, then therefore the gap of the walls is just equal to L. So we can assume that rod is just fitted tightly into the gap of the walls. Gamma is the Young's modulus of the rod, and alpha is the coefficient of linear expansion. Delta theta is the temperature change. So let us first of all discuss that what will happen if we increase the increase the temperature of the rod. So if walls were not present here, we can imagine that if we would have increased the length, increased the temperature of the rod would have expanded by a length of delta L, where delta L will be equal to L and alpha delta theta, where delta theta is the temperature change. So this is that length which rod would have expanded if walls were not present. Now, we can also say that these walls have restricted the rod to expand, and therefore the restricted length is delta L. So the strain developed will be equal to delta L by L, and it is equal to alpha delta theta. This is the strain developed in the rod. So we can see that these walls would be applying the force, compressive force on the rod, and therefore we can assume that the walls have compressed this rod by a length of delta L, where delta L is L alpha delta theta. Okay, so the compressive strain is delta L by L, which is alpha delta theta, and therefore stress will be Young's modulus into strain. So thermal stress is equal to, this is denoted by sigma, and it is equal to gamma into strain, where strain is this delta L by L and this is alpha delta theta. So sigma is gamma alpha delta theta. This is sigma, thermal stress. So this gamma is Young's modulus, this alpha is coefficient of linear expansion, this theta is that change in temperature. So this is the thermal stress, and to demonstrate the thermal stress with more clarity, I would be bringing a concept of composite rods in the next video. Thank you. Now in this example, we can better understand the thermal expansion and the stress developed due to that. So in this example, there is a composite slab made up of steel and copper bars, and the area of cross section of both are equal, and this composite bar is restricted between two walls, and let's suppose that the initial length of these two was, this is L01 and this is L02. This is the initial length. So this is the complete length of copper bar initially, and this is the complete length of steel bar. Now we have increased the temperature, and we see that this junction of both the bars moves towards copper by a distance of x. So we can say this is the final displacement of junction towards copper. Now if we imagine that a steel was independently expanding, then we can see that the total expansion in the steel due to temperature rise delta T would have been L01 alpha steel delta T, this complete. But the junction has shifted by a distance of x. This is x. Okay, so let's suppose that this is x1. This is x1 and this is x. So we can say that x plus x1 is equal to L01 alpha steel delta T. So x1 is equal to L01 alpha steel delta T minus x. So we can say that if steel was independently expanding, then it would have expanded by a length of L01 alpha s delta T. But in the real scenario, there is a copper bar which is restricting steel to expand independently. Therefore, the steel has not expanded completely. In fact, it has expanded only by a distance of x, as the junction has moved only by a distance of x. So we can see that while steel was expanding, this copper bar would be applying some force on the cross section of the steel, and we can say that due to this force, the compression has developed in the steel, which is x1. Now, why I am referring it as compression? Because I am assuming that if steel was independent, then it would have expanded this much, but due to the copper bar, it has only expanded by this length. So I can say that the restricted length due to copper bar is L1, which can also be imagined as the compression, as if the copper has compressed this steel by a distance of x1. Now in the similar case, if this junction was initial junction and it was here for the copper, so this length was initially L0, 2. We have already discussed. Now we see that finally the junction has moved by a distance of x. This is x. And if the copper was independent, then this length, it would have expanded independently, would be L0 to alpha copper delta T. And we can see that if it was expanding independently, then its copper junction would have moved from this position to this position. This is L0 to alpha copper delta T. But in fact, it has the junction is moving towards right instead of moving towards left. So junction has moved towards right by a distance of x. So we can see that due to presence of steel, the steel would be applying some force on the cross section of the copper, due to which this copper would be experiencing some deforming force. And we can say that due to this force, the junction should have been expanded till this level, but it has been compressed till this level. So we can say that this is the restricted length x2. So x2 in this case would be equal to x plus L0 to alpha copper delta T. So we have to calculate the restricted lengths in both the cases. And now the strain developed in steel is equal to this restricted length x1 upon the original length of the steel, which was L01. So this is equal to alpha s delta T minus x by L01. I am dividing this complete equation by L01. Now the strain developed in this copper is x2 divided by L0, this length L02. So this is equal to x by L02 plus alpha copper delta T. And the stress is equal to the strain into Young's modulus, we all know. We can see that the force applied by copper on steel and the force applied by steel on copper is same, action-reaction force, and the area of cross-section is also same. So the stress developed would be equal, and therefore we are equating the stress of steel with the stress of copper. So stress is gamma of steel into strain of steel, which is alpha s delta T minus x by L01 into gamma steel, and this is equal to stress in copper, which is x by L02 into gamma copper minus alpha copper gamma copper delta T. Now we have to find out this value of X. So we can just rearrange the terms and we can see that this we are taking this term here and this one here. So it is when it comes here, then it comes to be gamma S alpha S plus gamma Cu alpha Cu, and delta T is common, and at that side it would be X common, and it would be gamma Cu upon L02 plus gamma steel upon L01. So X is equal to gamma S alpha S plus gamma Cu alpha Cu divided by gamma Cu upon L02 plus gamma steel upon L01. So this is the final expansion in steel and compression in copper, or we can say that this is the shift in the junction. If L01 and L02 are equal given, initial lengths are equal, so we can rearrange again, then it gives to be gamma S alpha S plus gamma Cu alpha Cu divided by into this is L and divided by gamma Cu plus gamma steel. This is the value of L X. Okay, so this is a very important type of question as far as JEE Advanced is concerned, and in the next video I will be bringing much more interesting concepts of solids. Thank you.